Okay, our final talk will be by Kevin Burdge, telling us about how some black holes are born gently.
All right, I'm going to time myself to make sure I don't go over. Okay, well, I wanted to open this talk by saying thank you to Neil and Jane for probably the 3 most fun years of my life. I've tried to have something new to show you every year, and this year I have something completely new to show you. So I'm just going to launch right into it. The title of my talk is that some black holes are born gently. So this is a result related to a very famous black hole called V404 Cygni. I just want to highlight this image here was actually taken with the Chandra X-ray Observatory, and these are X-ray light echoes around that black hole after an outburst occurred in it. So it's an accreting black hole. And you can see an image of it up here. You're going to see more of those images. So I just want to outline some basic facts about V404 Cygni. This isn't just any black hole. It's actually a pretty special one. It's one of the first binaries with a dynamically confirmed black hole accretor. Let me explain what that means. So what it means to dynamically confirm it is when we look at the star orbiting the black hole, when it's moving towards us, the light is blue shifted. So we see the absorption lines go to shorter wavelength. And when the star orbiting the black hole is moving away from us, the light is red shifted. So this is what we call dynamical confirmation. It's just using Kepler's laws to infer how heavy that thing is that's making the star wobble. And in this diagram, they're showing it for a planet. The tricky part is planets don't make their stars wobble very much because planets are so low mass. The nice thing about black holes is they really make the stars move because they're quite massive. And so this object's very famous. So here's a Nature paper that's slightly older than me that basically, I'm just going to read the final sentence. We consider this the most persuasive case yet for the existence of a black hole. So this is really one of the original prototype objects. The other thing I want to point out is the orbital period in this system is 6.5 days. By my standards, that's long, but that's actually pretty short. The Earth takes 365 days to go around the sun. The star is whipping around this thing every 6.5 days. And the donor, the thing dumping matter onto the black hole, is evolved. And what that means is this started out as a star kind of like the sun. And normally, it would not have been putting matter onto the black hole. But then it tried to become a red giant. And the black hole had something to say about that. It said, no, you're not expanding any further. So that's a special property of this system. Another interesting thing from yet another Nature paper that I think is slightly younger than me is that there's a high amount of lithium in that star. Yes, indeed, I'm slightly older than this Nature paper. The reason that's a big deal is in astronomy, we talk a lot about nucleosynthesis. How do you make the elements in the universe? And lithium's a particularly tricky one to make because stars don't really make it. But for some reason, we keep finding things around black holes that have a lot of lithium. And the result I'm going to be talking about actually has some interesting things to say about this. The other thing that's really interesting about this black hole is the jet may be misaligned from the orbital plane. So when I say that, what it means is this jet coming out of the black hole doesn't seem to be aligned with the plane that the star is orbiting in. And that's actually a little bit unexpected because you expect the black hole spin axis to be aligned with the orbital angular momentum spin axis. And so here's a Nature paper slightly older than my oldest son talking about exactly that. So V404 Cygni has gotten a lot of attention over the years and still is. Also say it's the first black hole where we actually had an accurate distance. People measured a radio parallax to it. And understanding how this thing evolved and formed is still an active area of research. Here's a paper from last year titled An Evolutionary Model of the V404 Cygni System. So there are over 1,200 papers written about this thing. So you might ask, what was I doing looking at V404 Cygni? Because if you've heard my previous talks, you probably think I work on white dwarfs. Well, it turns out 2 of my best friends in this business, Kareem El-Badri and Aaron Kara, both work a lot on black holes. And in talking to them over the years, I also got a little bit interested in black holes. Kareem mostly works on these detached black holes, not the accreting ones. And I tend to like those because they're easy to understand. But working with Aaron here at MIT, she worries about accretion. And that is something I had always avoided studying because I thought it was too messy to really give you interesting constraints. But I got interested in accretion in white dwarfs and then consequentially black holes, and I'm going to tell you one of the reasons why. I've been building instruments, and so actually we recently bought this high-speed camera. I like taking movies of the sky. And I'm going to try to put this camera on the Magellan telescopes. And so I want to show you the kind of movies that I like to take of the sky. So you've seen this in my previous talks. Normally, I take movies of white dwarfs. And so this is an eclipsing binary with a 7-minute period. If you look at the movie, you can see this thing disappear every few seconds. It's obviously sped up. In real life, it takes 7 minutes. But that's the sort of thing I like to build. And I got interested in thinking about, could we use this to do something interesting with black holes? And so I asked, what are sort of the holy grail problems here is, can you tell apart an accreting black hole from an accreting white dwarf by taking a very high-speed movie of it? In particular, in the quiescent phase, which is when they're very hard to tell apart. And so I went out looking for basically a paper to see if anyone had ever taken a high-speed movie of a quiescent black hole. Turns out they did it for V404 Sig because everyone seems to write papers about this, and they actually found some interesting things. But me being the typical astronomer I am, the first thing I did is when I think about something, I go to Google Maps for astronomers. This is called Aladdin Light. I'm embarrassed to admit that when people ask me to meet at a coffee shop, I often pull up Aladdin and then go, oh, this is in Boston, not the galactic bulge, and have to switch back to Google Maps, because I use this every day. This is an old digital sky survey image of it, DSS. Now, the blue thing is V404 Sig. And then I went to a more modern image. This is from Pan-STARRS. And I was like, there's a second star like right on top of it. But maybe not that surprising because this is the galactic plane. And so I zoomed in and I turned on these little boxes called Gaia. These boxes are basically telling us about measurements taken with this Gaia satellite, which very precisely measured the motions and positions of stars over the sky. And this little thing here, you can just click on the box and see what the numbers are. And what I found is that the motions in two directions were -5 and about -8 for V404 Cygni. And so, of course, I clicked on the other box and I was like, those numbers are just about the same. I was like, they're moving with each other almost perfectly. That was a little surprising. I was like, I didn't know V404 Sig was in a wide triple. So this is a triple system. This is the accreting binary. You can't tell those two stars apart, like the black hole and the star. And then there's this thing way out there moving with it. And so I went to Simbad, which is another tool a lot of astronomers use. And I just listed all 1,261 references. And then I hit Control F and type triple. And there were 0 hits. And I was like, that's surprising. I did find one paper that mentioned, there's this pesky blended star that seems to be similarly reddened, and we wonder whether it's truly unassociated, but this was pre-Gaia. I also found papers like, we really want to form these systems in triples. It's too bad that none exist. They must all be white dwarfs. Guess what? One of the brightest black hole X-ray binaries was, in fact, a triple staring everyone in the face. So I immediately messaged Aaron and was like, did you know that it was in a triple? Nope. I messaged Kareem El-Badri, one of my other close collaborators, like, hey, I discovered this random fact. It's in a triple. And he goes, that's funny. There's this paper about triples. And I was like, yep, I already know that one. Let me tell you why this is a big deal now. So you can see the motions of all the stars in the field, the Gaia measured motions. And you can see these two things are moving in lockstep. These are actually really far apart. So in the image, it looks like they're really close. But because that binary, or the triple's so far away, that separation's actually about 3,500 astronomical units. That's 3,500 times further away than the Earth is from the sun. It's about 100 times the Sun-Pluto distance. It's way out there, orbiting with about 2 kilometers per second. So much wider than the inner binary, which is a little 6-day orbit. That's a big deal, and I'm going to tell you why. But the key thing to remember is the only 2 kilometers per second part. We'll come back to that. An amazing thing, and this is, again, just by accident that this is happening, is, so let me tell you a little bit of a story about stars. It's actually kind of hard to tell how old stars are. Unless they're very, very low metallicity or something like that, Stars don't age like people. People change on the outside as they get older, and you can kind of see them throughout their life progress. Stars, unfortunately for astronomers, most of the changes that happen are in the core, which we can't see. And it isn't until the very end of their lives that they kind of show us their age by trying to evolve and become what we call a red giant. Just by pure coincidence, this star, so what you're seeing on this plot is its radius and temperature, and this color bar is basically showing the age. It just so happens to have inflated to about twice the radius it was when it was on the main sequence. And that actually lets us get a really good age for this. This is the first black hole where we can actually measure the age of it pretty robustly. It's about 4 billion years old. Just total happy accident that it happened to be evolving in this stage of its life. So now let me tell you about the cool physics that we get out of this. So the reason that this thing being in such a wide orbit is such a big deal is it means you have to be extremely gentle when you form the black hole, because the orbital velocity is only about 2 kilometers per second. So it means if you prod the inner binary too much, it just goes flying off and leaves this thing behind. It's a very fragile configuration. And so I did tons and tons of simulations, and I found basically the biggest kick that you could give the inner binary and still hold on to this thing is about 5 kilometers per second. We call these things natal kicks. So the idea is we think when most black holes at stellar masses form, they come from supernovae, which are very violent events that eject a bunch of matter. It's hard to eject a bunch of matter like that and not impart momentum to the black hole that's left behind, unless you do it perfectly symmetrically. But I found in my simulations of trying to keep this system bound that even if you do it perfectly symmetrically, you still get into trouble, especially if the system started in a short orbit. And here's the reason why. If I took a metal ball on a string and I swung it around really fast and the string snapped, you would all duck because you wouldn't want to get hit in the head with a metal ball at that velocity, right? Well, it turns out that the progenitor of the black hole, if you started in a tight binary, is moving pretty fast. And even if it's in its own reference frame, it ejects the matter perfectly symmetrically, that matter is still going to go careening off at the velocity of the black hole. And that imparts momentum. Momentum's conserved, right? We all learned this in intro mechanics. And so you still end up kicking it. And so what you find is if the binary started in a tight orbit, the thing basically needed to collapse completely. You don't want to eject any matter. If you started the inner binary in a wider orbit of, say, 100 astronomical units, much wider than the current 6-day orbit, then you can eject a little bit more matter. You still can't do too much, but then you somehow need to get the thing into a 6-day orbit. And we think that may have happened through an interaction with this tertiary. But in the end, the key result is you can't kick that inner binary and keep a hold of this thing. So this is really demonstrated as probably the most robust evidence we have of a black hole that formed without any substantial kick. So let me talk a little bit about some key takeaway points. Let me just check the time and make sure I'm not going way over. I always talk much faster in my, I don't know where I put my phone. OK, anyway. 7 minutes. OK, good. 1 orbit of my favorite binary. So key takeaway point, the black hole in V404 Sig received less than a 5 kilometer per second kick when it formed, unless you contrive some very fine-tuned and improbable scenario. Like you can do stuff like say, oh, well, I'm going to eject the matter asymmetrically in the rest frame and impart a kick exactly opposite of that conservation momentum kick and get a net kick of 0. You have to do a lot of fine-tuning, I found in my simulations, to make those things work. So the easy conclusion is no kick. V404 Sig is between 3 and 5 gigayears old. We know the age because the tertiary is evolving. It probably underwent these things called Kozai-Litoff cycles. That's a fancy word for that outer tertiary's gravitational influence caused the inner binary to change its orbital configuration. This is actually a little bit important. You remember one of those earlier Nature papers about the misaligned jet? They said, oh, that must have happened because there was a kick that misaligned the black hole. That's not allowed anymore, but those gravitational perturbations actually naturally can cause the orbit to change its inclination and misalign potentially. And then I just want to say, this is kind of a remarkable thing. We realized we got really lucky in detecting this thing. If we had looked at it a billion years ago, we wouldn't have found it because the star that's now evolving and is twice its normal radius would have been too faint for Gaia to have measured the proper motion. If we look at it a few 100 million years from now, we also wouldn't have detected it because that star will be a red giant and completely swamp out V404 Sig. And if you look at it a billion years from now, you also wouldn't have found it because then it would be a white dwarf and too faint for Gaia to even see. Which tells us it's definitely worth looking for more of these. This was incredibly fine-tuned and lucky. They're probably actually tertiaries around most low-mass black hole X-ray binaries. And so that's exactly what we're doing. So we put in a Hubble proposal, which is under review, so it isn't accepted yet. I'm PI, Aaron's co-I, and Kareem is on it as well. And we're going to image a bunch of black hole binaries with Hubble to look for more of these. And let me show you some of the things I found in preparing that. So here's an image of some famous black hole that's accreting. It's this object right here. And suspiciously, this star has kind of very similar motion, but it's so well measured that it's like a 10 or 20 sigma discrepancy because the error bars are so small. And I was like, it's really weird that they lined up so well, but it's inconsistent. And then I flipped to the Hubble image, and I was like, oh, this is actually an unresolved binary. And the wobble caused by that binary exactly explains the discrepancy we see in the Gaia error bars. So this is actually a quadruple, I think, where you have this binary that's orbiting this accreting black hole in a much shorter period. This was just doing our homework to write the proposal, and this stuff was sitting in archival data. And I just want to say, this is the power of angular resolution, sharper images. The Giant Magellan Telescope is going to be a big deal for this stuff because your angular resolution goes as lambda over d, where d is the aperture of your telescope. This has a really big aperture, which means this image gets a factor of a few even sharper. And what that lets you do is not only resolve these binaries, but actually lets you measure the motion of these objects and constrain even these outer orbital periods and their eccentricities and things like that. So that's all sort of on the black hole stuff. I have a little sort of side thing I wanted to show. So last week I was at Caltech, and I'm very proud of this. I went to visit my favorite telescope, the Hale telescope at Palomar. And I got to climb in the prime focus cage. I'm very proud of this. So this is dangling 20 meters above the primary mirror. To give you an idea, I was up there. This is the mirror. And to give you a sense of how big this thing is, that's the inauguration of the telescope. Like, I was really up there. It was a very special experience. So yeah, I love telescopes, if you can't tell. Yeah. OK, that's all I had. Thanks.
Thanks, Kevin.
In that first early slide where you were showing the movement of a whole bunch of that, you just went by it.
Oh, yeah, OK, I know what you're talking about.
That one. Is that purely a coincidence? You said you started with that this happened to be the same direction as that one.
Yeah.
That determination takes a lot of serendipity, if you will, to...
Yeah, so this is definitely a serendipitous discovery, which I like to call, it's a euphemism for dumb luck. But I'll have a slide I can show you.
Go back to that slide.
Oh, I was going to show this slide, which is actually showing. So this is where we calculate the chance alignment probability. So we ask, what are the odds that this happened by accident? So here's if you plot the declination and RA proper motion of all the nearby stars. And you see these two are right on top of each other. There's not much out there. Already pretty low chance that their motions agree that well. But we said on top of that, let's double check and actually take a spectrum of it and check that the Doppler shifts of the lines agree. So in V404 Cygni, the Doppler shifts go blue and then red, but we can find the average Doppler shift to see how fast the system is moving in the third dimension. And then we checked the Doppler shift at that tertiary and found it also agreed really well. So we found the motion in the third direction agreed. And so we ended up computing a chance alignment probability, and we found it's about 10 to the minus 7. So it's about a 5 sigma result.
But the concern I had, who had a whole bunch of stars, there's bound to be a couple of them that have the same direction.
Yeah, so what we did is we basically asked how many stars do you have to check to find another one that agrees that well? So it's not just the direction, it's also the magnitude agrees really well. And so we asked how many stars do you need to check, and the answer is about 10 to the 7 stars or so.
Who was the one that actually made that discovery?
Of the tertiary, that was me looking at the image.
Was you?
Yeah.
So Neil, you see the 2 arrows at the center, the red ones. So find another arrow in that diagram that is as close, that looks the same, that has both the same length and the same direction.
I agree, but you're bound to have something similar. That's why I was
Even if there were something similar in that diagram, that close, this is astoundingly unlikely. I mean, yes, getting the radial velocities helps you to the 3rd dimension, but I don't need any persuading.
Yeah, I didn't either.
I agree. I'm just saying it's serendipity, blind luck.
Yeah.
Well, it isn't
Well,
blind luck, it's physics.
yeah, we calculated the luck part, and the answer is about 10 to the minus 7 are the chances of this happening by accident.
Say 10 to the minus 7 a few more times. I just wanted that to get, yeah, okay, yeah, so it's,
Thanks, Kevin. Great talk. Good to see this. I had a comment and a question. The comment is just, you keep referring to blind luck. I want to quote Pasteur, which is, fortune favors the prepared mind. So, and then I had a question, which is sort of, how automated can you make the search for triples? I mean, you're going to get all this data from this search. I mean, do you have are you going to use machine learning? Can you say a little bit about what fraction do you think you can actually detect of things that are there in your data?
Yeah, so the moment I found this, I wrote a pipeline to check Gaia around all of the black hole X-ray binaries, and that's how I found that one that was kind of close, but still 20 sigma off. There weren't any other obvious ones in Gaia. That's not a surprise because most of them are more distant. This is like one of the closest black holes. What we're going to do is we're going to image all of these with Hubble. About half of them, fortunately, people back in the 90s and early 2000s got pictures with Hubble. So all we're going to do is compare the pictures and see, is anything moving exactly together with the black hole? That's a pretty easy measurement. It's just measuring co-motion. For the ones that haven't been imaged, it'll take a couple years. If we use higher angular resolution imaging with things like the ELTs, for example, like GMT, we accelerate that process massively because basically your sensitivity to the co-motion just has to do with your angular resolution. But we're hoping to turn this into a cottage industry, basically. Hubble's going to be good for white dwarfs, so we're imaging in the ultraviolet there to basically look for white dwarf tertiaries that have been left behind the donors that finished their evolution. We're also using Keck adaptive optics to look for M dwarfs. It's much more sensitive in the infrared than Hubble, so we're also checking for low mass stars around them. It's actually not a big surprise. Black holes come from massive stars. Massive stars tend to be in binaries and triples and so on. So it should really come as no surprise that these exist. It's just surprising no one paid attention to this particular one.
If I could follow up with one more really quick question, which is, what is your current thinking on if you get hundreds of these, what that will tell you about the black hole formation process and how you end up having a process instead of handling?
Yeah, so the hope is, any one of these you find, you get upper limits on kicks. And so you start to really uncover a population where it's like, okay, at least these black holes all seem to have an absence of kicks. This is going to be actually in parallel with Gaia is actually going to find a bunch of detached black holes as well and get similar constraints. The most powerful constraints on the kicks are going to come from being able to measure eccentricities of those outer orbits. Because sort of the devil's advocate argument that a lot of people made was, well, what if these started out really close to each other and they had a kick that just barely failed to unbind the tertiary and sent it on some highly eccentric orbit and you just caught it at the outer part of the orbit? That requires a ton of fine tuning and almost certainly didn't happen. But the way you confirm it is you image it with GMT and check, is the motion radial like you would expect if it were on the outer part of an eccentric orbit? Or is it moving tangentially to it? So yeah, it's going to be studying the orbital dynamics. You won't be able to do what Andrea Ghez does and watch them go all the way around because the periods here are 70,000 years. You're only looking at a tiny little slice of the orbit. But when you get that kind of angular resolution, you could still do interesting stuff with that.
Was there another question over here?
Is it possible that the third system could have been captured after the supernova? Yeah.
So that's a very good question, and I've iterated through this a few times. So the answer is the following. In the field, the probability is exceedingly low. So space is very empty. The odds of things just randomly in the plane colliding and capturing something, that cross-section is tiny. But what you could imagine is, hey, this might have formed near the galactic center or in a globular cluster where the stellar collision rate is much higher and dynamical capture happens a lot. The problem with that is once you capture it, how do you get it out of the globular? Because the escape velocities of those are a few tens of kilometers per second. Same with galactic center. So you can't really give it the kick to get out of the environment. On top of that, because we know the age is only about 4 gigayears, it's also a bit young to have come from a globular. The one scenario that we are still considering is actually it may have formed in an open cluster. I think that's the last thing, and that we can't definitively rule out. So that is one potential possibility.
So going back to the beginning of your talk and the high-speed camera, can you, I didn't catch what you were going to do with the high-speed camera.
OK, I can tell I love talking about these things. So this is an amazing camera. For those of you who work in optics labs or things, this thing has 0.22 electrons of read noise mean, which is extremely low for something without any kind of avalanche gain. What I spend most of my time doing with these cameras is the following. I'll play the movie again. So normally I work on white dwarfs. And so I get light curves of them. And you can measure all sorts of amazing things with these light curves. And one of the most beautiful things you can measure is orbital decay due to gravitational wave emission. And so what I do is I use these high-speed cameras to get really nice movies of these eclipses so that I can time these sources, kind of like the Hulse-Taylor pulsar, except here the gravitational wave emission is orders of magnitude bigger because the orbital period's only 7 minutes instead of hours. So that's most of what I do with these cameras. I point them at what we call LISA gravitational wave sources to characterize kind of the relativistic behavior in them. For the black holes, what I was going to do, since we were talking about that, it turns out some of these show, well, V404 Cygni shows a quasi-periodic oscillation in quiescence at a 20-minute period when imaged at 5 seconds. So the hope is that there's some unique signature these might show in their high-speed light curves that white dwarfs don't. And if we could figure that out, we could survey the sky with CMOS-type sensors to look for more of them in quiescence. That was kind of the idea we were throwing around before we got distracted by the triple.
Just to satisfy my curiosity, I mean, what does high-speed mean?
Well, the camera itself, if you window, can go to 20,000 frames a second. We're thinking about some pulsar FRB work with that mode. For me, high speed, about a hertz, I'm pretty happy with for most of what I do.
Oh, I see. And that's high speed by astronomical standards, because you're not like looking at something for a long time to get a lot of light from it.
Yeah, by astronomical standards, more than once a decade is high speed to a lot of people. So.
I see, OK.
OK, any other questions for Kevin? Kevin, thank you very much. And while you're clapping, let me also just say that concludes our program. So let's thank all of our speakers again. OK, so thanks very much. And so those of you who are invited dinner guests, there's a reception for you next door. And everyone else, we'll see you tomorrow. Thanks very much.